Thanks, Silas, for the introduction. Today we will present you the EMC design essentials, mastering Varistors and common mode chokes. My name is Stefanie Birkenbach. I'm product manager for common mode chokes and filters for power lines.
And my name is Ashiro Chen, and I'm product manager for common mode chokes for data lines and low voltage.
And my name is Ben Dashu, and I'm responsible for the overvoltage protection devices.
Okay, so now Pengda will start with the presentation.
Okay, so here you can find an example of the EMC filter used to attenuate the electromagnetic noise. The circuit is composed by a fuse holder, a varistor, a discharge resistor, a common mode choke, and the X and Y capacitors. Each component has its own function. For example, the varistor is used to attenuate the overvoltage transient noise, and the common mode choke is used to attenuate the common mode noise. In the next slides, we will go into deep and explain the detailed characteristic of each noise and the corresponding protection devices. Due to the time limit, we are not allowed to present here all the components in this webinar. We are mainly focused on overvoltage signal attenuation and common mode noise attenuation. Here you can find the example of EMC filter used to attenuate the electromagnetic noise. The circuit is composed by a fuse holder, a varistor, a discharge resistor, a common mode choke, X capacitor, and Y capacitors. Each component has its own function. For example, the varistor is used to attenuate the overvoltage transient noise, and the common mode choke is used to attenuate the common mode noise. In the next slides, we will go into deep explaining the detailed characteristic of each noise and the corresponding attenuation part. Due to the time limit, we are not allowed to present here all the components. In this webinar, we are mainly focused on overvoltage signal attenuation and common mode noise attenuation. Okay, now let us to see some basic knowledge about overvoltage protection. Here you can find a good example. The circuit is connected with a power source, and we will give it a overvoltage signal. Okay, first the circuit exploded, and then the rest of flash is expanded to anywhere, which may cause dangerous situation like a fire. Therefore, we need overvoltage protection to avoid this kind of issue. Okay. The definition which we have defined before for overvoltage is very general. Of course, such abstract definition does not help us to get to know the detailed characteristic of overvoltage signal in each case, and moreover, we need also a standard definition in order to test our protective components, suggesting the right product for each specific case. So in this slide, you can find the international standard to define the overvoltage signal. Basically, the overvoltage is classified into three types. First, we have the surge, defined in a standard 61000-4-5. This kind of overvoltage comes normally from the nature, like the lightning, and is characterized by high voltage, high current, low frequency, and produce huge energy by each pulse. The second one is the EFTB, electrical fast transient burst. In this case, it's defined in the standard 61000-4-4. Different than the surge is characterized by bursts of pulses. Normally, this kind of pulses come from the industrial application, like connection and disconnection of the inductive charges. This kind of pulses is characterized by high voltage, low current, low energy, and high repetition. The last one is the ESD, electrostatic discharge. In this case, it's defined in a standard 61000-4-2. This kind of wave or pulses come normally from contact between two bodies. It's characterized by a voltage much higher than the other two kinds, but lower current, lower energy, and lower repetition. Okay, in this slide you can find an overview of all the surge pulses which we have mentioned before. Among all the pulses, ESD has the highest voltage, but it has much lower current compared to the surge waveforms and the EFTB waveforms. Therefore, at the end, it has much lower energy than the other two. Then the energy of EFTB is also quite high, and it can eventually reach to 1 joule. It's mainly because of the pulse duration is quite long. This type of pulse is composed of a group of small pulses, and when combined, they can reach to very high energy level. Okay, now let's look at all the protection components against the surge waves. Okay, here we have an overview of the surge protection components. On the right, we have the TVSP diode. It's a SMD component. It's smaller and its clamping region is relatively narrower. Next, we have the THT varistors. It's the biggest component among all the three, and its diameter can reach up to 23 mm. Finally, we have multi-layer varistor. It's also varistor, but used to SMD montage. Okay, let us to start first with the varistors. Varistor is mainly composed by three layers: an outer insulation layer made by epoxy, an electrode layer made mainly by silver or copper, and the inner single oxide core. At microscopic level, the core is made up of many single oxide grains. These grains behave like conductive regions for the current, while the boundaries between the grains act like barriers to current flow. When the voltage between two grains becomes sufficiently high, the current can forcibly cross these grains boundaries and move from one grain to another grain. For this reason, when the voltage between the electrode is low, only a small current, leakage current, can flow through the terminals. However, when the voltage is high, the current can pass through almost all the grains by crossing the boundaries between them. As a result, the current between the terminals becomes much higher. Okay, here we have an overview of all the electrical parameters from the datasheet on the EV curve. First, we have the leakage region. This is the region where the current has not yet reached 0.1 mA for 5 mm varistors, or 1 mA for varistor of other sizes. The voltage at this current is defined as the breakdown voltage, which is indicated by the blue lines. We have also in this area the working voltage, marked with the green lines. This voltage must be 25% higher than the operating voltage of the circuit. Between the breakdown point and the maximum current, we have the operating or clamping region. In this region, the varistors are considered to be already activated and are protecting the load against the overvoltage. Finally, the region after the maximum current point is the destruction region, where the component is close to failure. Starting from this slide, we will look at the multi-layer varistors. Unlike a THT varistor, here multi-layer varistor is based on SMD mounting. Their structure is very similar to the THT components. They have two electrodes, and from them we have the electrode layer parallel made by silver, and then these layers are extended into the single oxide core. The operating principle is also almost the same like the THT varistor. The current is flowing from one silver layer to another silver layer through the single oxide grains. The difference here is that THT varistors has only two silver layers, meanwhile the multi-layer varistors has multiple silver layers. In this table, you can find a general comparison between both types. Due to the size difference, the working voltage range, maximum current, and the energy capability of multi-layer type are much lower than THT types. However, the multi-layer type has faster response time and lower capacitance than THT one. Okay, starting from this slide, we will talk about TVSP diode. Unlike the varistors, which we have discussed before, TVSP diode is based on silicon PN junction. It has three main parts. The core is made by semiconductor chip, a silicon PN junction. Then the chip is protected inside of a plastic package. And finally, the copper electrodes are connected to both sides of the chip, and these electrodes are extended to the outside of the package, allowing its connection with the circuit. In the table, you can find an overview of the main characteristics of TVSP diode. In general, like I have already mentioned before, the TVSP diodes have a narrower clamping area than the varistors. Okay. On this slide, you can find the definition of the electrical parameters on the current voltage curve. In this case, we have taken the unidirectional component as an example. In the forward direction, the voltage must exceed about 0.6 volts for current to flow. This point is indicated by the red lines. In the reverse direction, we have the working voltage, which is marked with the blue lines. The corresponding current at this voltage is a leakage current, and this value can be found in the datasheet. Next, we have the breakdown voltage, marked with the green lines. This is the point where the current through the diode reaches to the value specified in the datasheet. It's considered that the diode is activated since this point and protects the circuit from the overvoltage signal. Then we have the maximum current and the corresponding climbing voltage, which are indicated by the brown lines. These are the maximum values allowed for the component. If passing this limit, the component is close to failure. Okay, here we can see how the components behave in the unidirectional and bidirectional cases. In the unidirectional case, the protection is asymmetric. In the current voltage curve, we can see that the voltage drop is around 0.6 to 0.7 volt in the forward direction. From that point, the voltage increases only very little as the current rises. In the reverse direction, however, the voltage must exceed first the breakdown point in order to flow the current. Once that point is reached, the increase in voltage with respect to the current becomes negligible. In the bidirectional case, the protection is symmetric. In the current voltage curve, we can see that the voltage must always exceed the breakdown point in order to flow the current, regardless of the direction of the current. The EV curve behavior is identical in both the forward and reverse directions. Okay, now let's look at protection against an ESD process. In this field, we have mainly two types of components. The first is a TVS diode, and the second is the ESD suppressor, which are varistors. All of them are specially designed for ESD protection. You can see that for the diodes, we have divided them into 3 families, and for the varistors into 4 families. Why are there so many families if they are basically the same type of components? Let's take a look. If you remember the general overview of the components which were presented before, you can see that the component for ESD pulse protection have in general lower capacitance. But why do we emphasize so much the capacitance? Why is it important for ESD protection devices? Okay, capacitance is related to the insertion loss. ESD signals are much more critical on data lines. That does not mean that the power lines do not experience ESD signals. ESD pulses do not affect the power lines as much because of their relative lower energy compared with the surge pulses. But they are especially important for data lines because the signals are much smaller and more sensitive. In data line application, insertion loss becomes important because if it's too high, it can cause data loss during transmission, affecting the normal operation of the circuit. Insertion loss changes with the frequency. In the graph, you can see how the insertion loss curve evolves as a function of the frequency. The calculation of this parameter can be found in the equation. In general, the insertion loss depends mainly on impedance. At the same time, the impedance depends on 3 properties: resistance, inductance, and the capacitance. Resistance of this component is almost constant with frequency. Meanwhile, the inductance requires a rotational structure, which does not apply in our case, so its value is practically negligible. Finally, we have a capacitance, which plays an important role in this situation. In the graph, you can see that the higher the capacitance, the lower is the resonance frequency. The insertion loss starts to become significant from the resonance point onward. On the right, you can find a table with different data applications, together with the resonance frequency and the corresponding capacitance range. On this slide, you can find an overview of the diodes designed for ESD protection. We have 3 different series: standard, high-speed series, and the super-speed series. As the name already mentioned, the standard series has the highest capacitance, the high-speed series has the intermediate capacitance, meanwhile the super-speed series has the lowest capacitance among 3. In addition, the electrical properties differ from one series to another series. Customers need to check the datasheet to find the most suitable option for their application. For TVS diodes, there is an interesting point to discuss. Some of our TVS diodes can have snapback effect. As you can see in the graph, the component requires an additional voltage to reach to the breakdown point, and then it follows a curve similar to that of a normal diode in the climbing area. This phenomenon occurs because when the component is mounted on the PCB, a parasitic transistor can appear once the voltage rises to a certain level. As a result, the diode remains in the leakage region even though the voltage across its terminals has already reached to the breakdown voltage. However, when the voltage reaches to a certain critical point, the parasitic transistor effect will disappear, and the diode starts to behave like a normal diode again. In addition, as you can see in the graph, at the same current level, diodes with standby FET have always lower coming voltage, which means a better protection. The only disadvantage is that the diode needs an extra voltage to become active, but this voltage is negligible compared to the voltage during a transient pulse event. On this slide, we can find an overview of the ESD suppressor. We have divided them into 3 series. As in the case of diodes, the main difference lies on the capacitance. The standard series has the highest capacitance, meanwhile the femto series has the lowest capacitance. The ULC series has intermediate capacitance. The last one which I would like to mention is a multi-array varistor. The internal structure of this series is like 4 varistors in parallel. This helps to meet some special customer requirement, for example, when the design is very compact and the space between the paths is very close. In addition, thank you for the new technology and the improvement of a production process. Now it's also possible to produce multi-array varistor with lower capacitance value. Okay, since now, my colleague Steffi will start to present the combo choke for power applications.
Okay, so now we will talk about combo chokes. First about the basics, and afterwards we will divide between the applications of mains line and data line. Can you show the picture? Okay, here just as an example, we brought also one of our biggest combo chokes, and on the left maybe you see this really small black dot. This is one of our smallest combo chokes, just for comparison about what we are talking. Okay, so why do we need a combo choke? What are the benefits? The main reason to use a combo choke is to suppress the combo noise, maintaining the signal and power integrity, and ensure the compliance with the limits at the EMC test. So, if you go with your application to an EMC lab and get results like this, you're failed. The noise is above the limits given in the standards. So how can we fix it? We need a filter for this. While thinking about a filter, you maybe thought using 2 inductors, 1 for each line. But this would also influence your desired signal. If you're using a combo choke, this will not happen. And we will see later why. When we are talking about noise or filtering, you will hear about common and differential mode. To understand how a combo choke works, we need to clarify these 2 modes. So differential mode describes the signal or noise that appears on 2 conductors carrying equal currents in opposite direction. This is the normal operating mode for signal or power transmission, where the current flows on one path and returns to the other. Common mode describes the noise that appears in the same direction on both conductors. The return path is typically to ground, chassis, or parasitic capacitances. How is a combo choke built and how does it work? A combo choke consists of minimum 2 windings on one shared magnetic core. Its purpose is to attenuate the common mode currents while allowing the differential mode currents to pass unaffected. Now with this, we have a current carrying conductor and a magnetic field is generated. The direction of this magnetic field can be determined with the right-hand rule. So, what happens in common mode? The current flows in the same direction on both lines. The magnetic fields produced by those currents are co-directional. What happens in common mode? The current flows in the same direction on both lines. The magnetic fields produced by those currents are co-directional and therefore increasing the magnetic flux. This results in a high impedance or resistance that chokes or blocks the common mode noise from passing to the circuit. In differential mode, the signal or power where the current flows out on one line and returned on the other. This is where the currents create a magnetic field in opposite direction. So this cancels each other out. And the chokes offers a very little impedance to the desired signal and leaves it almost unaffected. While comparing different common mode chokes, you maybe recognized already different kind of winding styles. When we are talking about winding styles, we divide between sectional winding and bifilar or multifilar winding. If the windings are wound side by side, this is called bifilar. Also, if we're talking about 2 wires, or multifilar for more. The sectional winding is separated from each other. So one winding is on one core half and the second on the other. The closer the 2 windings, the smaller is the stray field, which you can see here in green. And therefore also the leakage inductance is smaller. Compared to the stray field of a sectional winded part, the fields for bifilar ones are much smaller. How these styles are used in our products, you will see in a different section. For power and data line common mode chokes, we need to consider different aspects. When selecting the best common mode choke for a filter, first determine the frequency of the noise. Different core materials perform better in different frequency ranges. Manganese zinc is the primary material for common mode chokes and performs best at lower frequencies. The nickel zinc ferrite is suitable for higher frequency noise. And nanocrystalline cores offers a wide frequency range and additionally a good temperature stability. You will see more information in the part of the power line chokes with some real examples. Okay, let's have a look at some datasheet parameters. If you want to select and compare different common mode chokes, it's also important to compare the test conditions, not only the nominal value. You can see here an inductance graph of one of our common mode chokes, and depending on the frequency, we would have a different inductance. The nominal inductance should be defined in this horizontal area so that there are less effects. For test frequencies, we can also use a suggestion from the standard IEC 6938. Depending on the nominal inductance value, they recommend different test frequencies. So as example, for an inductance starting from 1 millihenry, they define a test frequency of 10 kilohertz. What should also not be neglected is the accuracy of the measurement equipment. So the accuracy of a LCR meter is also depending on the inductance and the test frequency. The next parameter is the rated current. Here it's also really important to take care of the test conditions. Often different rated temperatures are used, and so it's not possible to compare the parts one to one. Even in our product range, we're using different values. You can find the rated temperature in the test conditions here with this at 70 degree in this example, and this is the maximum ambient temperature at which an inductor can carry its rated current. We are also showing the temperature rise. In this example, maximum 55 Kelvin. So the important is that the ambient temperature plus the self-heating of the part is lower than the defined maximum operating temperature. And if you have a higher ambient temperature in your application as the rated temperature, you can check the possible current with the derating curve. So for example, if you have a 90 degree of ambient temperature, you can use 80% of the defined rated current from the data sheet. Sometimes we are also getting questions about saturation. So what is the saturation of the common mode choke, and why are we not showing this in the data sheet like it's done for inductors? First, I want to show the differences between common mode chokes and inductors. As explained in the beginning, our desired signal runs in differential mode. That means the signal is going to one line into the system and back on the other line. In a common mode choke, in differential mode, the magnetic flux is in the opposite direction and cancel each other out. Due to the resulting flux of the currents being almost zero, the choke will not go into magnetic saturation. under normal operating conditions. For a usual inductor with just one wire, this will not happen. So let's check a real example. There's no saturation effect in the differential mode due to the field compensation. This is this black line. And in red, you can see a fast saturation in common mode. Usually, this shouldn't be a problem because the common mode noise currents are compared to our saturation current low. They are usually in an area of some micro to milliamps. So now we will go a bit deeper into the common mode chokes for mains power line application. We will start with the safety requirements from the IEC standard. We will see which winding styles we are using and why, and come back to the leakage inductance and the core materials, and also see the effects of different designs. According to the standard, the IEC 60938, we need to keep defined creepage and clearance distances, depending on the rated voltage. The clearance distance is the shortest distance in air between the two conductive parts, so this means between our two wires. And the creepage is the shortest distance over the insulation of two conductive parts. The creepage distance is depending on the pollution degree and the material group of the insulation material. As I already said, the common mode choke can be winded in two different winding styles, bifilar and sectional. And for mains line chokes, we usually only use the sectional winding style. The reason are our safety requirements for creepage and clearance distance. For example, if we want to use a 230 volt AC, we need a clearance of 2.5 millimeter and a creepage distance between 1.25 millimeter and 4 millimeter, depending on the insulation material and pollution degree. So with the bifilar winding style, we can't keep these distances easily. And with the sectional winding style, we create also the wider stray feed and so the higher leakage inductance. The leakage inductance is responsible for the differential mode attenuation. Earlier I said the common mode choke does not affect the desired signal, which is the ideal behavior, if we would have a perfect symmetric winding and no stray effects. It's not the real case. So in case of power line applications, our desired signal has a frequency of 50 or 60 Hertz. So even if we have a higher differential mode attenuation, we will not influence the 50 Hertz signal, as the attenuation starts at a much higher frequency, which you can see here between 100 kilohertz and 1 megahertz. So in best case, our common mode choke could attenuate common and differential mode noises. And maybe you don't need an additional differential mode filter choke. So let's check the effects of the core materials with some real examples. Here we compare similar toroidal core chokes, but with different core materials. The size of the cores is similar, and also the number of turns and the wire diameter. In the table you can already see that even with the same parameter of the wire, the inductance is quite different. And this is also reflected in the attenuation graphs. The green curve shows the nickel zinc material. The best attenuation of this material is in the higher frequency, with a resonance at almost 20 megahertz. In black, the nanocrystalline material, the amplitude here is not that high as for the other materials, but the attenuation works in the wide frequency area. And in red, the manganese zinc material, which is working the best in the lower frequencies. It's quite often that an inductor or common mode choke is only chosen by the inductance value. Here I want to show that this is not the best way. All three of these components have an inductance of 1 millihenry, but the attenuation could be different depending on the frequency. So if you want to choose the best component for your application, it's always better to have a look at the attenuation or impedance curves and check the attenuation at the needed frequency. And due to the different core materials, we also need different number of turns for a similar core size to get the same inductance. With this in mind, it could be also possible to have a similar performance with different sizes. A nanocrystalline core could have, as example, a smaller size for similar performance to a manganese zinc core. And so it's also possible to choose the common mode choke according to the dimensions. And last but not least, as said at the beginning, also the design or the shape could have an influence on the filter. In this case, both of the parts have the same inductance of 1 millihenry and the same core material, but the attenuation is different for different frequencies. The reason are the different winding geometries. Each inductor has parasitic capacitances between the windings and between each turn, and this can be used to change the filter behavior. The winding of the frame core choke is at separated chambers on a bobbin, and this reduces the parasitic capacitances, and so the resonance frequency is shifted to the right. And this effect is not only in common mode. We can also use the design to create a higher leakage inductance and differential mode impedance due to the parasitic capacitance. And now I will hand over to my colleague Ashiro, and he will give you some more information about the data line and DC common mode chokes.
Thank you, Steffi. Now we will talk about common mode chokes, but in this case for DC and data applications. So we have several series in our portfolio, and this could be a bit overwhelming in the first interaction. So how can you choose the right common mode choke for your design? Here you see that all of our series are organized in DC and data. Some series are specifically designed for DC lines and some series for data lines. Sometimes you can find a solution for both the DC and the data application. This flexibility comes from one of the common mode choke characteristics, which is the winding style. That could be bifilar or sectional, as it was explained before by my colleague. And as it was explained earlier, this winding style has an effect and an impact in differential mode signal, while also influencing the key parameters such as the insulation level. When it comes to reduce noise in low power or data lines, there are several alternatives. But a common mode choke integrates real inductance into each line, acting both in differential and common mode. This makes them ideal when reliable and repeatable filtering is required in electronic designs. This comparison here is explained more in detail in the application note link that you can find on the right side. We have summarized the benefit of using common mode chokes by some of the most popular applications and in which frequency the noise could be located. This table here is valuable when we don't have the tools or the possibility to measure and analyze the noise spectrum directly. For example, in power supplies, one of the main noise sources comes from the active switching of the transistors. This can generate sharp edges and high frequency disturbances that easily couple into both the input and output lines. A common mode choke is highly beneficial here because it provides strong attenuation of these unwanted signals while maintaining the integrity of the DC power path. So this table is not a final answer, but a very useful guide to make the first filtering decision with confidence. With the common mode chokes for data lines, we can find different applications. In this slide, we show two different examples, one for USB and one from Ethernet. As you can see, the common mode chokes that are targeting data lines are always present in the differential signals in the applications. Compared to the data chokes, we have the DC chokes that you can see here in our real applications. And for the DC filter applications, the rated current parameter is one of the focus. Now that the current will be applied constantly on the windings. The recommended PCB design is to place the common mode choke as close as possible to the connector. In this way, we block the noise at the entry and exit point of the system, preventing it from propagating through the PCB. In this example here, this is an LED lighting matrix where we had some flickering, and we decided to implement a common mode choke based on the constraints of our design. Sometimes we can find the so-called mixed application, And as you can see in this example, we have a signal or data line, but also a DC line for power. In this case, we can find different solutions, as it was explained before. And in this case, we implemented the SL5 series due to the rated current value and its ability to provide both the common mode and differential mode attenuation at the desired frequencies. For a general case, when selecting a common mode choke, several factors must be considered. The designer should have the application constraints clear and the different parameters. As you can see here, we show one of the first parameters that the designer should have in mind, which is the working current and the rated voltage. As you can see, all the parameters can be found in the datasheet. Next, it is essential to clearly define the application, whether the common mode choke is for data, for DC, or for both. The winding style, as it was explained before, plays a key role in selecting the right common mode choke, because as you know, either the bifilar or sectional will have an impact in the final application. For the next step, we must remember that the signal is transmitted in differential mode, and the noise we aim to suppress is in common mode. This is important to choose a common mode choke that has the highest common mode impedance at the noise and its harmonics frequency. And for the data choke, that has to be a really low differential mode impedance at the transmission frequency. For DC applications, a high impedance in both modes could help reject all the noise, common and differential. Finally, the designer needs to verify that the DC resistance included in the choke will not affect the signal or the voltage level, because we will always have some drop. So it has to ensure that the EMC performance meets the required standards. Here we show some guidelines for the implementation of the common mode chokes on the PCB. So now I would like to say a few words about the news we have in our portfolio. First, as you know, we are constantly expanding our portfolio with new solutions. Here you can find the two latest releases. One is in the series CNSW. We developed a new size, especially for CAN applications. And for DC chokes, we developed a series expansion with different sizes and different packages to target the different applications that you have. For more details, we invite you to visit our website. Also, in the area of power line chokes, we are working in our series and also expanding them. In this case, you can see here that the CMB HV will get a higher voltage rating up to 1000 volts AC and 1250 volts DC. Additionally, the series will be certified by VDE and ENEC. In the last year, there are two new updates for the overvoltage protection components. First is that all the series VD, the THT varistors, as it was explained, have upgraded the maximum operating temperature from 85 degrees to 105 degrees. The second update is about the VS, the multi-layer varistor that you saw before. Since the release of the PCN, all the products are upgraded to the lead-free version. Thank you for the time, and now we will go through your questions.
Yeah, thanks for the presentation. Now we'll come to the Q&A session. Before we start with the Q&A, I will share the handout from the presentation today, and now everyone can download it. Now, Pengda, are you ready for the questions?
Yeah, of course.
Perfect. Then we start with the first question. Okay, this one. How often can a varistor trigger? How does it age?
Okay, this is a quite interesting question. This information is already included inside of our datasheet. In the second page of our datasheet, you can find a graph with the name PLD. Its complete name is a pulse lifetime derating curve. And inside you can find how many pulses can the varistor so far can the varistor protect the circuit before its failure. And normally, if in the graph you can only see the theoretical number of the pulses which the varistor can support. If you really want to double check in practice, for example, in your application, I really recommend that you make an EV curve measurement in order to double check its leakage current area and see if there is a huge change between the normal varistors and the used varistors. If there is a big change, for example, the leakage current has increased a lot, then I would like to recommend to change the varistor by the new one.
Thank you, Pengda. Then next question. This one. Does the input capacitance value drift as varistors age?
Okay. Honestly to say, we have never done a test about the change of a capacitance respected to the varistor age. However, if we think from a theoretical level, after each climbing pulse, there is always a material degradation in the inside of between the grains of the zinc oxide at the microscopic level. So from my point of view, it makes that the medium becomes more homogeneous. So in principle, I think the capacitance will decrease a little bit. But since that the distance between the electrodes are not changing a lot, the decrease of the capacitance will not be very big. But honestly to say, this is just a theoretical hypothesis. We have never verified with the experimental data with the measurement.
Thank you. Then next question. Any idea about increase in varistor leakage current as varistor ages?
Okay. This question is very similar to the first question which I have answered, but in another direction. Normally, in the case of varistors, after each overvoltage signals, there is, like I have already mentioned before, there is always a material degradation internally. It implies that the boundary between the grains is becoming weaker and weaker. So in this case, it implies that the leakage current will also increase significantly when the varistor is old and it has already used for many overvoltage signals. So it means that the leakage current will increase with the varistor age.
Thank you. Then next question. Hi, so if it understand correctly, it's possible to parallel resistors, isn't it?
It's possible to parallel varistors. I see that there is some design is using it. And yeah, in many applications, I have also seen the similar issues. But honest to say, I never recommended to connect the varistor in parallel. Why? Because the main issue is that the current always tend to take the weakest varistors. I mean, the overvoltage signal always tend to run through the weakest varistors. And it means that when there is a small difference in the climbing voltage, in the leakage current, in the climbing voltage of the varistors, the current will be always focused on the varistors where the leakage current is higher, where the climbing voltage is lower. So by this way, the energy of the whole overvoltage signal will be focused only on one component, and this varistor will quickly destroy, I would say. So I always recommend not to try to connect in parallel and distribute the current. Always try to select the suitable varistors for each case.
Thank you. Then next question. This one. Let's see. What is the isolation versus frequency between varistors in multi-array?
Multi-array varistor, yeah.
Yeah. Is this data given in datasheet?
Honestly to say, when you are talking about the isolation versus frequency, I'm not quite sure if this isolation you are talking the climbing voltage or if you are talking about the other isolation resistance, and so on. If you are talking about isolation resistance, I will say that this is a given value in a standard. We always follow the IC standard and make the corresponding isolation test. The isolation test can only tell you, okay, if the varistor can pass this standard test condition or not, but it will never tell you what's the exact isolation resistance. And on the other hand, if you're talking about coming voltage, I will say that we have never done a test of the coming voltage versus frequency, because we're more, in this case, we're more focused on a capacitance value.
Thank you.
And another thing is that if you are talking about coming voltage, the frequency of the overvoltage signal is always, I will say, similar, and there is not really a good comparison between the repetitive high frequency signals and the overvoltage signals. There is not so much sense to compare.
Then next question, is there application note with calculations with combo choke and caps for combo chokes filter, leak filter?
In this case, you can find the application note inside of our website. In this case is the AMP 137. You can search this application note easily in our website.
And I think also the application note.
Yeah, 146. Yeah.
146, yes. You can find this on the homepage, on the landing page AppNotes. Okay, then I would say one last question. Choke.
Okay, I see a message from Jagdish. Yeah, it is a signal isolation,
yeah.
not a safety isolation. Honestly to say, when you talk about the signal isolation, I'm not quite sure about the signal isolation which you are exactly referring, because normally when we're talking about the varistor, we're always talking about coming voltage and about the coming current. So if you can make more in detail about signal isolation, please send us by email some examples and so on. Maybe we can try to answer in much more details.
Okay, thanks. Then I can see a lot of more questions in the chat. So yeah, Pengda and Stephanie and Ashiro will answer them via emails in the next days. So thanks for joining. Thank you, Pengda, for the
thank you
for the answers of the questions. So yeah, hopefully we see us on our next webinar. Have a nice day and bye bye. See you soon.